In my job, I often look at molecular dynamics simulations, though it is really not my main task. There are many tools to visualize these simulations, or as they called professionally also trajectories, but in my opinion most tools are either hard to use or produce a bit ugly results. And I mean, this is fine if I'm the only one looking at these produced animations, but sometimes I want to show the trajectories to other people and maybe even advertise my work a bit. So it would be nice to have a solution that I personally can work well with and that also produces great animations. So I thought a pretty nice way to do this would be to use a little program called Blender. Blender is an amazing, fully open source 3D software, which is more designed towards more artistic projects, but Blender has a built-in Python editor and a Python API. So basically everything you can do within the graphical user interface, you can also code up as a Python script that interacts with the API. Surely you see where this is going, right? That means I can do scientifically accurate representations of the simulations that I run, while also leveraging the 3D abilities of Blender. And now I want to code up a script to visualize my molecular dynamics trajectories and render some beautiful animations. So now we are in Blender and I really don't want to lose much time. On the top you can see that we have several tabs. Right now we're in the layout tab, but I want to go of course to the scripting tab where we can write our own Python script. The first thing to note is that the API is exposed via this BPY module, which is pre-installed in the local Python environment in Blender. And the first function I want to define is just something that clears the entire scene of every object, so we have a clear canvas to start from. And that is quite simple. First we have to select every object and then we just delete them. Then we just call the function and run the script. And as you maybe saw in the left window, every object disappeared, which in this case means it worked. On the bottom left you can also see a log of every action that happens inside Blender. So if I just add a sphere right now, you can see in the bottom left that we executed the action bpy.ops.mesh primitive UV sphere add. And we can copy that call and use it exactly like that to repeat this action. So that's how you can very simply build a program that just repeats what you did manually. At the top of the script, I now add the first of many constants, which is the path to the trajectory file itself. Before we continue with the scripting, I should probably talk about the data format of the trajectory files. In principle, it is just a sequence of individual geometries at each time step. The first line in every geometry is the number of atoms that are in the geometry. In this case I have 6 atoms per geometry. The next line is just a random comment that can be any kind of string. In my case I just write down what time step it is, and then I have as many lines as atoms, 1 line for every atom. And the first thing I write in every line is just the species of the atom. In my case I only have oxygen, so that is denoted as O, and hydrogen, which is denoted as H, the chemical symbols of the species. And then there come 3 numbers, and these 3 numbers are just the X, Y and Z position of the atom. And in the end there's one empty line, which I added just for readability, and then the next geometry comes. Equipped with that knowledge, we can now start to write a function that passes the trajectory file. And the very first thing we do is to read the number of atoms in the molecule, since that number is conserved in all of the trajectory. That way we can also deduce how many lines we have per geometry. And then for every geometry we can just pass the lines that describe the geometry to a function that actually builds the molecule in Blender. Which means that now we have to write the function that builds the molecule. First we have to parse the lines into actual Python objects, so a list of species and a list of coordinates. And now we want to add a sphere to represent each atom, so let's write first that function that adds a sphere with some material and some predefined radius to the 3D environment given a species and a location. To add the sphere itself, we employ the primitive UV sphere add function. You can see that I added some keyword arguments like segments and ring count, which define how well resolved the sphere is, which I will just define as constants of the script. For the radius, I will employ the van der Waals radius of each atom, which is just a value you can look up online, but I write it here as a constant dictionary which I can use to look up in the function itself. Every atom should also have some color to differentiate the different species, and I will get the color using a get or create material function which we need to define later, which basically just gets or creates a material. So if the material already exists in the project, it just returns the material. Otherwise it returns a new material which is specific to the atom species. And then what we do with the material is that we just assign it to the sphere. Then now let's define the get or create material function, and it's basically just if or else. So if the material name exists in the project's data, then return that material. Otherwise create a new material with that given name and return that. When I create the material, I say that the material should use nodes, which is just some Blender specific way to define a material. And by default, this nodes material has a principled BSDF shader, which I can use to change the default color. Let's look quickly at how you would find this out if you didn't know this already. To show you, I created a new sphere and I can add a new material to the sphere. And the material will also appear by default in the shader editor as a material that uses nodes. As you can see here, I have some tooltip that tells me exactly what the corresponding Python API call would be to change that attribute. Going back to the script now, we can assign the default value for the base color of the principled BSDF shader by using a color that we predefine in a constant dictionary. As before, you can just look at the tooltip to find out the Python attribute that you need to modify. Now we are just missing the dictionary of the default atomic colors. The color is defined as a RGBA tuple. And for the colors themselves, I choose the standard default colors that are normally used. So for hydrogen, that is just pure white, and for oxygen, it's pure red. We still need to actually call the create atom function. And after one minor correction, we can build molecules without any problem. Now I also want to add a function that adds cylinders between two given positions. These cylinders should represent that two atoms are bonding. It works pretty much in the same way as adding the atoms, but instead of the primitive UV sphere add function, we use the primitive cylinder add. The radius of the cylinders is now just another constant of our Python script. But now we need to figure out the right position and rotation for each cylinder. Position is quite easy. The cylinder needs to be exactly in the middle between the two given positions. So we just add the positions together and divide by 2. For the rotation I want to use quaternions, since Blender provides some quite useful functions for working with them. But before that, we need to set the rotation mode of the cylinder to quaternion. And now the vector.toTrackQuad function actually does all the hard math for us. We just tell it that we want to align the z-axis of our cylinder along the connection vector between the two positions while keeping the y-axis as undisturbed as possible. We chose the z-axis because cylinders in Blender are oriented by default along the z-axis. And we could choose either the x or y axis to leave undisturbed because cylinders are symmetric along that plane. After figuring that out, we just need to assign some materials to the cylinders. And we can just steal the logic from the atoms, but instead of every bond having a different material, they all have the same global material, which we can just call bond material or something like that. And of course now we need to add the bond material to our list of materials. I chose a very dark gray as the color. While fixing another error, I realized that I didn't clear the scene every time, so I had a lot of copies of the atoms. This should fix it. For testing purposes, Let's add bonds between every atom. Beautiful, but it works. Let's set up some proper bonding information and use that to define where the bonds actually go. And it works first try. After this was sorted out, I just set up a basic scene using Blender itself. So I added a camera, a light source, I changed the color of the background, and I also changed the color management, the camera types and so on, so all these little details. And then I just copy pasted everything that appeared in the action log of Blender into a new function which I called setUpBasicScene, so it is reproducible. The Blender logging is quite verbose with the keyword arguments of every function, so unfortunately it looks a bit messy. With these changes implemented, an example render of my trajectory now looks like this, which I think is quite nice. Finally, we just need to extend the code to automatically render each geometry in our trajectory file. After running the script, we obtain a lot of images in the render path we specified. We can combine these different images using FFmpeg, for example, to render out the animation as a MP4. And looking at it, it looks like this, which is okay, but I think we can still improve upon it. My idea is the following. So far we have been manually deleting the scene and rebuilding it for every frame, with slightly modified coordinates for the atoms. This works, but it doesn't really take advantage of the built-in animation system that Blender possesses. In my second approach, I now want to build the molecule once and just update the coordinates of the existing 3D objects. The positions of the atoms I set, then as keyframes properties at the corresponding frame number. I won't bore you with the details, but the code is on my GitHub and the link is in the description, in case you're interested in the details. Working with the Blender animation system has some advantages. For example, we can now also animate other properties, for example the camera scale, which can give it a nice zooming in or out effect if we need it. And something that I find nice, but it is strictly not necessary for a scientific animation, is to have some motion blur, since now Blender knows about the velocities of each atom. Now we can render the final animation. And the final result looks like this. I leave you with this and say goodbye and thanks for watching. Bye!